Hello, good afternoon, everyone. I hope that you are having a good day. I am Dr. Lina Mahjazi, and I am going to teach you the last three lectures of the Power Engineering course. Well, I do hope that you have been enjoying this course so far. In the last bit of the course, we are going to discuss together the electric machines concepts, and these include the electric motors and the electric generators. Today we are going to start by talking a bit of introduction of the electric motors. So let us get started. So our lecture about the electric motors is going to be divided into several topics. Today we are going to highlight the general working concepts of electric motors. We are going to discuss the three-phase motor, including its basic components and the stator windings, the rotating magnetic field. Later on, we are going to discuss how to analyze the equivalent circuit for the induction motor and how to apply some performance analysis on the induction motor. Well, let me first start by telling you that electric motors are available in our daily life. We use them. They are available in home appliances, in, let's say, electric fans, in cars, in industry. So these are one of the famous electric machines. And in order to understand how they work, we need to go to some basics. We really need to go back and understand what is a magnetic field, and then we are going to discuss its relationship to the working principle of electric motors. So remember a magnet. As you can see over here, it has two poles, the south pole and the north pole. Remember that two similar magnetic poles repel each other, while opposite magnetic poles attract each other. You know that the magnets, they have a continuous force around them, which is known as the magnetic field, and you can see it over here by these lines, which are created as loops. And this field actually enables them to attract other materials. So what you can see over here is the lines of force, and the line of force, they are used to represent magnetic field, and they travel from the North Pole to the South Pole, and sometimes we call them the magnetic flux. Now, why we are talking about the magnetic field? Because they will reveal how the generators and the motors use this magnetic field in order to generate electricity, as well as how to generate mechanical motion. So the basic idea of an electric motor is really simple. So imagine you put electricity into it at one end, and an axle rod rotates at the other end, giving you the power to drive a machine of some kind. How does this work in practice? To find the answer, well, we need to go back in time almost 200 years. So suppose you are taking a length of ordinary wire, making it into a big loop, and lay it between the poles of a powerful permanent horseshoe magnet. Now, if you connect the two ends of the wire to a battery, the wire will jump because it's gonna move. When an electric current starts to creep along a wire, it creates a magnetic field all around it. And if you place the wire near a permanent magnet, this temporary magnetic field interacts with the permanent magnet's fields. You'll know that two magnets placed near one another either attract or repel. In the same way, the temporary magnetism around the wire attracts or repels the permanent magnetism from the magnet, and that's what caused the wire to jump. So as you can see over here, it all gets back to the relationship between a magnetic field and electric field. So the link between electricity, magnetism, and movement was originally discovered in 1820 by the French physicist Ampère. You might have heard of his name so far, and it's basic science behind an electric motor. But if we want to turn this amazing scientific discovery into a practical bit of technology to power our electric powers and toothbrushes, we've got to take it a little bit further. Now, the inventors who did that were Faraday and William Sturgeon and Henry. And in the next slides, we are going to understand how electric energy produces magnetic energy and how these two produce mechanical energy, which we call electromagneto-mechanical process. Now, suppose we bend our squarish U-shaped loop, so there are effectively two parallel wires running through the magnetic field. One of them takes the electric current away from us through the wire, and the other one brings the current back again. Because the current flows in opposite directions in the wires, the left-hand rule tells us, or the Fleming's left-hand rule tells us, the two wires will move in opposite directions. In other words, when we switch on electricity, one of the wires will move upward and the other will move downward. If the coil of wire could carry on moving like this, it would rotate continuously. So this is the fundamental concept of rotation through electricity, and would be able and would be well on the way to making an electric motor. But that can't happen with our present setup. Why is that? Because the wires will quickly tangle up. So imagine if we keep on switching the polarity, the rotation, the direction of the rotation will continue to change. But this will cause the wires to tangle up. Not only that, but if the coil could rotate far enough, something else would happen. Once the coil reached the vertical position, it would flip over. So the electric current would be flowing through it in the opposite way. Now the forces on each side of the coil would reverse. Instead of rotating continuously in the same direction, it would move back in the direction it had just come. So imagine an electric train with a motor like this. It would keep shuffling back and forward on the spot without ever actually going anywhere. So as you can see here from this diagram, this simple experimental kind of motor, it consists of a magnet, and as electricity passes through the loop over here, there is going to be a magnetic field, and because there is a magnet on the outer part of the loop, it will either cause the magnetic field to repel or to be attracted. And notice over here that these brushes, they carry the current to the commutator, and the commutator over here reverses the current in order for the direction of the rotation to flip. Now, let's get back to our problem. So there are two ways to overcome the problem of the tangled wires. One is to use a kind of electric current that periodically reverses direction, which is known as the AC. And in the kind of small battery-powered motors we use around the home, a better solution is to add a component called a commutator, okay, to the ends of the coil. All right. Now, in its simplest form, the commutator is a metal ring divided into two separate halves, and its job is to reverse the electric current in the coil each time the coil rotates through a half turn. One end of the coil is attached to each half of the commutator. The electric current from the battery connects to the motor electric terminals. These feed electric power into the commutator through a pair of loose connectors called the brushes, made either from pieces of graphite or thin length of spring metals, which, as the name suggests, brush against the commutator. With the commutator in place, when electricity flows through the circuit, the coil will rotate continually in the same direction. So that previous example is a very simple experimental motor, such as this isn't capable of making much power. What we can do is, in order to increase the turning force or the torque that the motor can create in three-way, we can either have a more powerful permanent magnet, or we can increase the electric current flowing through the wire, or we can make the coil so it has many turns or loops of very thin wire instead of one turn of thick wire. Well, in practice, a motor also has the permanent magnet curved in a circular shape, so it almost touches the coil of wire that rotates inside it. The closer together the magnet and the coil, the greater the force the motor can produce. So, although we've described a number of different parts, you can think of a motor as having just two essential components. There is a permanent magnet around the edge of the motor case that remains static. It is called the stator of a motor. And the inside of the stator, there is the coil mounted on an axle that spins around at high speed, and this is called the rotor. The rotor also includes the commutator, and the rotor and the stator are, both of them are magnets, and they generate magnetic flux using the coil windings of permanent magnet. The rotor is usually mounted on a bearing supported shaft, and it can be connected to any mechanical load or to a prime mover if that was a generator. So in between the rotor and the stator, you can see that there is an air gap over here, because of course otherwise they will be in touch with each other and the rotor will not rotate. So as a general knowledge for motors, the torque and the mechanical rotation is achieved by the stator and the rotor magnets. The stator and the rotors, they are magnets which could be either permanent, or then they can be created by passing current through their copper windings, and in this case we can consider them as electromagnets. And normally the current in electromagnets must be switched on and off with respect to the rotor position. This is either achieved through a mechanical commutator, as we have discussed before, or through a power electronic converter that we will discuss later on. But this is the fundamental working concept of a motor. If you would like to see an animation of how an electric motor works, please go ahead and see the video over here. It is really a very interesting video. I personally liked it. You will understand better the working mechanism of electric motors. Okay, so let us discuss now the construction of induction motors and talk a little bit more about the material that they are made from. So as you can see here, you can see the stator on the outer part, and inside is the rotor. The stator frame consists of laminations of silicon steel mostly, usually with a thickness of about less than half a millimeter. Lamination is necessary for the fact that since a voltage is induced along the axial length of the steel, as well as in the stator conductors, the laminations are insulated from each other, usually by a varnish layer. Well, this breaks up the conducting path in the steel and limits the losses, which are also known as eddy current losses in the steel, which you have probably discussed before with Dr. Tony. The stator coils are normally made of copper. Round conductors of many turns per coil are used for small motors, and rectangular bars of fewer turns are employed for larger machines. The coils are electrically insulated. It is a common practice to bring only 3 leads out to a terminal block, whether the winding is connected in Y or in delta. So you will also be hearing back the Y and the delta connection, or the star and the delta connection. The magnetic part of the rotor is also made of steel laminations, mainly to facilitate stamping conductor slots of the desired shape and size. And in most induction motors, the rotor winding is of a squirrel cage type, where solid conductors in the slots are shorter together and at each end of the rotor iron by conducting end rings. And in such machines, there is no need to insulate the conductors from the iron. Um, well, remember that in any case, the rotor is very rugged and is also economical to produce, in contrast to rotors requiring electrically insulated windings. The shape of the slots in the rotor can be designed to provide a variety of torque speed characteristics, and it all depends on the type of application that the motor will be used in. In general, the electric motors can be divided into two main categories: the DC motors, which are based on DC power, and the AC motors, which are based on AC power. The DC motors were the first type of motors widely used, and the system's initial costs tend to be typically less than AC systems for low power units. But with higher power, the overall maintenance cost increases and would need to be taken into consideration. It is also worth knowing that the DC motor's speed can be controlled by varying the supply voltage and are available in a wide range of voltages. The most popular types are between 12 and 24 voltage. Some of their advantages include easy installation, speed control over a wide range, quick starting, stopping, reversing, and acceleration, high starting torque, linear speed torque curve, and so on. The DC motors are widely used and can be used from small tools and appliances through to electric vehicles, lifts, and hoists. Some of their types include the brushed DC motor, the brushless DC motor, and the stepper DC motor. The brushed motor, this is the most traditional type of a motor and is typically used in cost-sensitive applications where the control system is relatively simple, such as in consumer applications and more basic industrial equipment. We have discussed the name where it comes from, the brushes. So these are the brushes, which basically participate in reversing the current polarity and hence the rotation. The brushless DC motors alleviate some of the issues associated with the more common brushed motors and are mechanically much simpler in design. The motor controller uses a Hall effect sensor to detect the rotor's position, and using this controller can accurately control the motor via current in rotor coils to regulate the speed. And the advantages of the brushless motors is that they have a longer life, they need little maintenance, and they are highly efficient. Whereas their disadvantages that they are a bit higher in terms of cost and more complicated, require more complicated controllers to control their speed, and they are generally used in speed and positional control with applications such as fans, pumps, compressors, and where reliability and ruggedness are required. The stepper motors over here, they use an internal rotor which is electronically manipulated by external magnets. The rotor can be made with permanent magnets or a soft metal. As windings are energized, the rotor teeth align with a magnetic field, and this allows them to move from point to point in fixed increments, and that's why they are called, it is called a stepper motor. On the other hand, AC motors are highly flexible in many features, including speed control, and have a much larger installed base compared to the DC motors. Some of their key advantages are low power demand, controlled acceleration, you can adjust their operational speed, you can control their starting current, you can adjust the torque limit, and they have reduced power line disturbances. Some of their type include the very famous induction motor, the synchronous motor, and the linear motor. The induction motor over here, this motor uses electromagnetic induction from the magnetic field. We will discuss it later on in more detail. It produces electric current in the rotor. So the magnetic field, which is generated in the stator, produces an electric current in the rotor, and hence the torque. And these are the most common types of AC motors, and they are very important in industry due to their load capacity, with single-phase induction motors being used mainly for smaller loads like used in household appliances, where their three-phase version of these induction motors are used more in industrial appliance applications, including compressors, pumps, conveyor systems, and lifting gears. The synchronous motor, this type of a motor, the rotation of the rotor is synchronized with the frequency of the supply current, and the speed remains constant under varying loads. So it is ideal for driving equipment at a constant speed, and are used in high precision positioning devices such as robots, instrumentations, machines, and process control. The stator is similar to that of the induction machine, consisting of a cylindrical iron frame with windings, usually three-phase, located in slots around the inner periphery. The difference is in the rotor, which normally contains an insulated winding connected through slip rings or other means to a source of direct current. The last type of AC motors we're going to discuss here is the linear motors. Today is going to be a lot of talking because we are discussing some backgrounds about motors, but things will be more practical, or let's say mathematical, later on. So the linear motors, these electric motors feature an unrolled stator and motor, producing linear force along the device's length. In contrast to cylindrical models that we have previously discussed, they have a flat active section over here, featuring two ends. They are typically faster and more accurate than rotatory motors. Let's talk a little bit more about the brushless motor. What is done over here in this type of motors is that we essentially turn the brushed DC motor inside out, and now have the permanent magnets on the rotor and the electromagnets on the stator for a brushless DC motor. So the stator phase currents are now turned on and off with power electronic switches. Now, note in this case that we need a rotor position sensor to tell the controller which phase to energize, so which of these magnets to energize at any particular time. So the brushless DC electric motors are also known as electronically commutated motors. The controller provides pulses of current to the motor windings that control the speed and torque of the motor. And normally this control system replaces the commutator in brushed DC motors, which is used in many conventional electric motors. And to understand how the electronic converter of the commutator work, so the principle is that for the brushed motors, it doesn't require an external controller, as the change of magnetic field polarity is implemented through the brushes, making and breaking the electrical pathway through the windings and achieving continuous rotation in one direction. Now, for some applications, that's good enough, but if we want to be able to change the speed of the motor or reverse the direction of rotation, we need a drive circuit. This can be as simple as just reversing the direction of current flow to make the motor turn the other way. Now, to change speed, we would alter the voltage using a potential divider, with speed being proportional to voltage. However, reducing the voltage in this way is inefficient, as normally voltage dividers do not reduce the total current flowing. So to enable the speed to be varied, we need a sort of a transistor that can deliver the required power and can be switched on and off by a control signal. So as you can see over here, transistors or diodes can be switched on and off in order to change the currents of the different magnets inside the stator. So before you guys have a break, let us talk in general about the relationship between the input and the output power of an electric motor. So as you can see over here, if we supply an electric power to a motor, no matter whether it is AC or DC, we call this the input power. After that, there might be some losses inside the device itself, such as if we use a power converter, which might not be required for all types of motors. There is another type of power losses in the electric motor itself, and this include the copper losses, the iron loss, the friction and the windage loss, and there might be also some other losses in the magnet or the commutator. Now, the final the final power is the output power, and that output power is fed to mechanical loads. These could include anything basically from pumps to hoists to conveyors to washing machines to compressors. So normally you wouldn't see, or in a practical motor, the output power is less than the input power, and that is all due to the losses inside. And what we have just discussed now is called the power flow. So you may take now a break, and we will continue later on after the break.